Welcome to session number 11 in the series Digital Circuit Design using ADS. It has been a day I didn't do the video. Okay, so let's get back to what we are doing. We designed a full adder and we tested that full adder, and we concluded that one of the topology was doing far superior to the other one, and that was a very basic topology which I want to show. So under arithmetic circuit full adder 1, yeah, so that was the one which was performing the best in terms of delays. So I'm going to do a very quickly a high-speed version of this. So the main topic of this session is not this full adder, but we have to quickly move on to shift register. So very quickly let's complete and test the high-speed full adder. Right, so I'm going to take this cell, copy cell, and I'm going to paste it. So I'm going to just do a full adder 1, and I'm going to rename this as HS and put it in the high speed folder, and I'm all set. Okay, so unless there is one already over there, seems like there is already one over there. Cancel. There is one, so let me just delete this one. Okay, so now it's going to be okay. Copy cell, and then I'm going to do full adder HS. Okay, so it should have gone here. Okay, so now I'm just going to replace these paths with high speed paths, and that's going to be very quick. So I hope there is a 3 this adder. If not, there will be a, okay, there is. Okay, next I am going to go into this, and this one is 2, this one is 4, let's say this one is 4, this one is 4, 6, 6, fine, and this can also be done 6 for a pull-up. That's the modification on 3 input NAND gate. 2 is okay, there's nothing special in 2 which I have to do, and these are also okay. So let me just see this one. Okay, so this is 2 and 4. Now let me make this 6 and 2. Fine. Okay, so we already have a symbol for this. We're just gonna modify this one. Sorry, modify this symbol, just add a text of HS, insert text, I'll put here HS, done, and save it, close it. Then I'm going to copy the test full adder also. So I'm going to say copy cell, and I am going to just copy the test full adder, and here I want to name this as HS, and I want to put this in this folder, high speed folder. Okay, and then I'm just going to replace this with HS, and this I'm going to make 2 femtofarads each. Right, and this is operating at 2, so I'm going to operate it at 20. So at that point this will be 24 picoseconds, and this will be 1 picosecond, and rise time and fall time is 1 picosecond. And so this is done. Then I'm going to change this one to 49 picosecond, and again this is 1 picosecond, and this one is also 1 picosecond. Okay, and this one is 5 gigahertz. This is going to be 99 picosecond. Rise time 1 picosecond, fall time 1 picosecond. Okay, so we are all set. And then instead of simulating for 2, so I'll simulate for 200 picosecond in steps of 1, maximum time step of 1 picosecond. Maximum time step of 1 picosecond. And the next thing I'm going to do is, I really want just the models for FinFET. So these are the models for FinFET. Control C, Control V. I'm going to put them here, and I'm going to throw this one out. So we are all set for simulation. So I'll just hit the simulate button. Unless there is a blunder I have done, I have no issues. There will be a small warning regarding substrate or something. Okay, meanwhile I'm also going to copy the same test full adder. So this is the one which I am interested in, right? Control C and Control V. Okay, now here is the glitch. Is it behaving properly? Just 1 second, let me fix it out. Let me put the video to pause. Okay, so it seems like this is not acceptable, right? So what am I going to do? I am going to try the other topology, right? So I'm going to try the other topology. See out. Okay, let's see. Is it okay? 1 0 0 1 1 0 1 0 0 0. Okay, let's see if this is okay. So this is 0 0 1 0. So 1 0 1 2 3 4 5. What is this? What about this one? I'm not receiving this waveform correctly, right? Okay, so let's fix that first. There's happening something with the time period on B. Okay, so it has to be 10 gigahertz, sorry. Okay, so now if that's being said, let's simulate this again. Okay, looks okay now. Okay, so this looks okay now. But what I want to do is I want to implement the other one also. There are rounded edges over here, right? There are rounded edges over here. So this response is similar to what we simulated for the other one, right? So for a low speed, we simulated this, right? And for high speed, we have this, right? Okay, so what happened was, okay, so now I also implemented the other version, the other topology. Let me just cancel this. Okay, the other topology, if you remember, is this one, right? And I had a medium speed version of it, and that medium speed version was not working as good as the other topology, which was let me see, which was this one, right? So with 130 nanometer, this technology was working much better compared to this topology. But at high frequency, I have implemented the other one, which one looks like this one. Okay, so this at high speed is one thing, and let's see how it compares to this one, right? So what I'll do is, first of all, we will do the simulation with this. There is a test bench here, right? Okay, so let's do the simulation with the one which was performing good in case of 130 nanometer, which is this topology, right? So let's just simulate this. Okay, and this was our response. Now let's say I'm going to replace this topology with the other one, right, which is this one, right? And let's see how it compares with the different topologies. So I'm going to change the simulation settings, change the sorry, not over here, so I'm doing mistakes here. Okay, so this is what we simulated, and now we want to test this one, isn't it? Okay, so I'll just change the data set. Why is it going to that one? No, this is just messing up. Just 1 second. Let me just fix this one so that we are not in a confusion. And we were talking about this one. So this is what we simulated, right? Okay, I don't want to mess up the data sets. Oh, okay, so this is what we had. Now the idea is to change this one to a different topology, which is, and resimulate this in a different data set. Apply, simulate. Okay, now I'm going to do this. Make a copy of this, right? And I want to replace all of these, right, with these HS1. So for example, I want to replace it with this one, right? So what I'll do is, I don't want to disturb the display, so I just copy this portion, delete this side. Okay, just change these. Okay, okay, okay. So now if you compare these two, what happened over here? Okay, this is not A. A has to be at the top. Hang on a second. A is at the top. Okay, so now if you were to compare these two, you will find that Okay, so corners are better on the C out. What about the adders? Okay, so this one, how it compares to this one. Okay, so this one is one topology, this one is another. We do not have this tail. Okay, we do not have these tails, but then the delay is better in case of the ones with the tail, right? Yeah, so it seems like, though I don't have this tail thing, but this is far more delayed than this one. So I think that this topology is going to work better than this topology again. So it really depends on your choice. Alright, so we will see when we do a look ahead carry adder, right, with number of bits, the delay becomes important. So maybe this one will fare better than that one, though it looks like this one is cleaner than that one. So basically that completes my comparison on high speed full adder. This I was operating at 20 gigahertz maximum frequency. Okay, so now I want to do one more standard cell, and that cell is going to be an mux gated D flip-flop, and that mux gated D flip-flop I'm going to use in a parallel to serial conversion, right? So mux gated D flip-flop, so I'm going to take a D flip-flop and just alter D flip-flop with a mux gate, right? Okay, so let's do that. Okay, so I'll take a D flip-flop, which I will find under flip-flops, and there is a negative edge triggered. So this is a master slave D flip-flop, right? I'm going to say copy cell, and this I'm going to say is going to be medium speed. This one going to copy in the same folder. So this is going to be mux gated DFFMS in the same folder. I'm going to copy. So that's a that's going to be the one which I'm going to alter. So just here I am going to put a mux, right? And the 2:1 mux is in the transmission gates. So if you go to 2:1 mux, 2:1 mux is over here. So this mux I'm going to place here, and I'm going to give VDD and ground. F5. Sorry, I want to move the text, so F5 is to move the text. Okay, let's give it a supply. So name the node. This is going to be VDD. This is going to be ground. Okay, and when it is low, the D has to go through. So basically D will be interfaced with this one, and if it is high, then I'm going to load the data. So I am going to make another pin here, and I will call this as, so this is 7th pin, and then there is a 8th pin. Oh, I have collected wrong. Okay, so there is a 8th pin which is going to be load. So 7, 8 are the new pins. One is D, so I'm going to name this as D load or data load. So this is going to be the data, and this is going to be the load. So this one is wrong. So this load basically is going to go to this one, and D load is going to go to this one, and this will be VDD. So this will be VDD. Okay, so what I have made is a mux gated D flip-flop, right? And I'm going to test that at maximum frequency of 1 gigahertz. Okay, now I'm also going to make a copy of this. So I have it two pins here, 7 and 8. 7 is called deload and 8 is called load. So I'm going to modify the symbol of this. Okay, so if I go to mux gated, open the symbol, I need to add here a load and deload, right? So I want to put here deload and load. So just bear with me. Load and deload. Okay. Okay, so I am going to move this a little so that I can adjust one more pin. That will be sufficient. And I will insert a pin. Insert a pin. And I'll call this as deload. The pin names have to match. So this is deload. Okay. And then I will have a load pin, which is over here. Okay, and then I'm just gonna copy this. Sorry, I'm just gonna copy this. Okay, this is deload. This is D. So this is going to be D load. Come on. This is deload. And this one is called load. This one is VDD. Right. And I will call this one as load, and this is already load. Okay, so we are done with the symbol for this one, and we can check this, right? Okay, so what we want to check is either I can receive a D input or a D load input depending on load, right? So I'm going to take a D flip-flop test bench, test DFF. I'm going to say copy cell. I'm going to copy test DFF. Okay, and call this one as text mux DFF ms in the same folder. And we have test mux DFF in the same folder. And over here I'm going to put here mux DFF, mux DFF ms. Okay, couldn't find, so don't worry. Let's locate that mux gated DFF. So that's over here. I'm going to throw this one out. F5. So I have a Q bar coming out of this, which I borrowed from here. That's okay. Then I have a VDD and I have a clock. So this is the clock, and I'm going to load a 0 whenever the load comes, right? So whenever the load comes, I'm going to load a 0. Okay, so this is operating at 2 gigahertz. This is D input. Okay, and then this is load. Okay, so D is much smaller than the clock frequency, which is 2 gigahertz. And then I'm going to put a D load at 1 gigahertz or 0.5 gigahertz. Okay, so this is going to be the load. So whenever the load is going to be high, okay, whenever the load is going to be low, then the output will respond to D. And whenever the load is high, the output will respond to D load, which is 0. Okay, and okay, so let's hit a simulate. Oh, I forgot to put load, name of the node. So this is the name of the node, load. I might to resimulate. So I'll resimulate this one. Okay, first of all, I'm going to look at clock D. Okay, so this is going to trigger on the falling edge of the clock. So falling edge comes over here. So everywhere falling edge is where the decision is taken. And then I'm going to look at load. So in this case, okay, load is a reserved keyword, so I'm going to change this. I'm going to say is feed. I don't know if feed is a reserved word. Okay, feed. Let's simulate this again. Okay, don't worry about this one. So I have a feed rather. Okay, and this feed I want to make green color and bold. Okay, so on the falling edges all the decisions are taken. So there are 2 falling edges over here, and it responds to D when feed is low, otherwise it is 0. So let's look at Q. Okay, so in this case, let's separate this out. I'm sorry about that. And let's adjust this thing, which is the bottom axis, from 0 to 2 in steps of 1. Okay, so basically what it says is when the feed is high, then 0 goes out. But when feed is low, then it acts as a regular D flip-flop. Right, so the output responds to input. So when again the D becomes smaller, so basically, so D is low. So here it responded, here D is high. So D is low. Okay. Okay, this is because of the master slave thing, right? So it makes sense. So these two cycles are coming from when the D is high. It's going to cause the load. When the load is high, right? Then it's going to respond to D. And when the feed is low, it's going to respond to D. When the feed is high, it's not. And this one is coming because of the master slave configuration. So I hope you understood what I'm saying. So this circuit is behaving as I want it to, right? So let's very quickly make a what you call a high-speed version of this. Okay, so to make a high-speed version of this, I'm just gonna copy mux gated DF. So I will say copy cell mux gated, and I will add a subscript of HS and put it in a high speed folder under flip-flops and say OK. So under high speed folder I have got mux gated D, here over here, and I'm going to just change these names to HS. Okay, so I have turned this into a high-speed version. So everything is HS. Right, so I'm done. I'll just modify the symbol to reflect that this is high speed. Insert text. I'll put here the text which says this is a high speed version. Fine, so now I'm going to test it. So to test it, I have done a test mux D flip-flop, so I'll copy this cell. Okay, change the name to HS and put it in a folder which is going to be flip-flop high speed. Okay, so test text mux DFF, right? So here I'm going to change this to HS, and here I'm going to load this with 2 femtofarad, sorry, and I'm going to bump up this stuff. So this is going to become 20 gigahertz, and that means that this is 24 picosecond, and the rise time is 1 picosecond, and the fall time is going to be 1 picosecond. Correct? So this one is altered. Now this one is 5 gigahertz. So this is going to be 99 picosecond. Remaining is going to 1 picosecond rise time and the fall time. So that's done, and then this is the D. So D is for 0.125, so it's going to be 1.25 gigahertz. This is going to be 399 picosecond. Sorry, 399 picosecond. Rise time is 1 picosecond. Fall time is 1 picosecond. Okay, so now let's look at Q. I have to just go inside and copy the FinFET models. Control C. Sorry, unnecessary mouse clicks, I'm sorry about that. Control V, and I am going to throw out this one. So we are all set for a high speed mux gated D flip-flop. Oh, okay, this is going for 16. I have to just go for 1.6, and we will go in 1 picosecond. Okay, save. I'm going to stop and release simulator because that's not what I want to do. Okay, so I'm going to simulate this again. And I'm going to copy the same display file. So in medium speed I was using, so let's do this. In medium speed I was using text mask, so which is generated over here. So I'm just gonna copy this one and I'm gonna just place it here. Okay, so what do you see? Same stuff, it's just that it's much higher frequency. That's it, nothing special. Okay, so we have done a high speed mux gated D flip-flop. I'm going to use this to make a parallel to serial and serial to parallel converter in the next session. Thanks a lot.